Hello, welcome back to our course Quality Management in Applied Statistics. This is Ulrich Weber and we are talking about random variables today in our third lecture. And at first, let's talk about why do we need random variables and the distributions. Well, the reason for that is fairly simple. We've always said I can calculate my probability to roll a 6 on my die just by the number of outcomes, so 1 over 6. But what if not every number has the same probability? So if each outcome aj, so 1, 2, 3, 4, 5, 6, has a different probability, and we call those probabilities here fj. Well, in that case, we have to find something different. So we could say the probability for 6 is just the probability function f of 6, whatever that number is. Okay, let's look at random variables a bit more in detail, and we're going to use the combinatorics from last time towards the end as well. So let's go into it. So what is the idea of a random variable? Basically, we want to understand a bit more how we create models of something that produces just randomness, random numbers, like data samples that we analyze that contain randomness in them. So let's say we've got this symbol here, x. It's just a symbol for a outcome of our system, a result of our random system. And this is our random variable. And we can say, okay, the outcome, when this system kind of produces some random result, is a number, because we always need to calculate with numbers, and so we associate this outcome here, any of the outcomes are possible, with a real number. That is kind of the idea of a random variable. And in most cases, that's kind of straightforward. So for the dice, for example, I can associate the outcome. I'm rolling a 1. I can associate that just with x equals 1. So I say my random variable produces the number 1. Then it's simple to associate, and likewise, if I roll a 5, then x is 5. That's easy. Quite intuitive. With other things, it's maybe not quite as intuitive, but we can just make something up. So heads and tails with a coin, well, it doesn't really matter, to be honest. The main thing is we need a real number. So here I said tails is a 0, but tails could also be a 5 and heads could be minus 17. It doesn't matter at the end of the day, but normally we just take things that are a bit more intuitive, like 0 and 1, I think, are more obvious choices. Okay, so as always, there are two different types. Let's first talk at discrete random variables, because as you see, an example being dice, it's a bit easier to think about them. So what does our symbol x here, what conditions does it need to fulfill to be allowed to be a random variable? Well, firstly, there has to be an existing probability for every outcome of x. That if x is equal to this outcome, then this probability has to exist, meaning it can't go to infinity or contain any other singularities or problems for calculation. This probability needs to be between 0 and 1. Yeah, so obviously probabilities add up to 100%, so it has to be between that range. Also, all the probabilities together, like if you sum them up, add up all outcomes, we have to be equal to 1. Yeah, we can't have more than probability of 100% of 1 for anything to happen. Okay, that's the set of 3. Doesn't sound too complicated, and that's all we need. So there are 2 things now for discrete random variables that I'd like to introduce to you. One is the probability mass function. Big word, PMF, we sometimes say. All it means is I've got a function f of j, and we already saw that on the introductory slide. And f of j just simply gives us the probability for outcome aj. Yeah, that's all it is. So if we say like a 6 has a 30% chance, then this is f of 6. Yeah, nothing more fancy than this. It just gives us the probability for this outcome. And yeah, you kind of get the idea, I guess. If the 1 has a chance of 10% or 0.1, then 0.1 is f of 1. So quite simple function. It just gives us the probabilities for each outcome. We talked about cumulative we talked about cumulative distributions at the very beginning in the first lecture, and here we've got the cumulative distribution function, the CDF. I'm normally gonna kind of label them with a capital letter, so small letter, low caps, F is the probability mass function. The cumulative one is the capital F, f of j, and that is like the summed up probabilities for all outcomes smaller than x. Yeah, you probably remember, we'll see that graphically in a minute. Okay, so let's look at this. So, for example, a probability mass function could look like that. We've got different outcomes. Yeah, this axis is my x. X equals 2, x equals 3, and so on up to 12. And the height here, I should have labeled this graph, sorry about that. This is my f of j. And there you can see probabilities around 5 to 15%. And yeah, we seem to meet all the criteria. So for each outcome between 2 and 12, we have a probability that's between 0 and 1. So they're all positive, and they, yeah, if you just believe me, they add up to 1. Okay. Interestingly, and this is kind of what I mentioned in the first lecture, the relative frequencies in the very beginning, the HJs, they are our best guess for the probability mass function. And especially if we go to large numbers of samples, like if you test, or if you have a huge data set, n goes towards infinity, then that converges. Yeah, so that's what people do. They take a big sample to like determine something, and then they calculate the relative frequency, and that's kind of what we assume is the probability mass function then, yeah, with a small error that we can control by the size of the sample. Perfect. The corresponding CDF looks like that, the discrete one. It's just to scale, so the blue bars are still the same as the ones we just saw, yeah, between 5 and 15%. Yeah, those are the blue bars, and all I'm doing now, I'm adding them up. Yeah, so let's for example look here at 3. The CDF is basically the blue one at 3 plus the little one here from 2. That one goes on top. And number 4 is the blue one of number 4 plus the whole CDF of number 3 going on top here. Yeah, so it adds up, and we've seen that with cumulative relative frequencies, we get a function that's like going up, 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 and heading towards 1. Yeah, meaning everything sums up to 1. Here, everything seems to be fine. Yeah, we can define this probability. The CDF is monotonically increasing, so we can never go down because we're always adding more and more. To the left, we start at 0. Yeah, that's true. Here's our start, and we finish at 1. Yeah, that's also true. Here we finish. Those are kind of the fixtures, and every CDF has to follow these rules. Okay. How do things change if we look into continuous variables? What's different? Let's think about a thermometer, for example. So now we are more thinking of intervals rather than individual values, because there's so many values, an infinite number. You can't really say, oh, it's exactly that temperature. It's more like, the needle is somewhere in between 10 and 12 degrees or something. So what we need is like the probability to be in a certain interval needs to exist. Yeah, that's kind of an interval from A to B. Those probabilities still need to be between 0 and 1. Yeah, just like every probability, and they need to add up to 100%. And for a continuous function, you remember that from mathematics, the sum is like the integral. We'll see graphically it's the area under the curve. Okay. Also here we've got the same names more or less. So it's called the probability density function here instead of probability mass function. The idea being, if you are with a discrete random variable, then you get like little rocks, little items. Yeah, there are outcomes. They have a certain mass. Yeah. So these are AJs. They all have like a certain weight, like a normal stone would have. Once we're in continuous, like we are now, you got like a sheet of some material. You can't really talk of like the mass of like certain bits, like it's not really well defined. So the easiest is to talk about density of the material. Yeah, it's just an analogy, kind of inspires the name. So the probability density function PDF, meaning density means immediately continuous random variable, and yeah, it's basically defined as this one here. The probability of x being in this little interval dx. And we can also create the cumulative distribution function, which will be the same as in the discrete case. It's just the integral up to this point x. Yeah, so also increasing. Let's look at this. So probability density looks, for example, like that. That is the probability density function. Like that's a normal distribution. That's, or Gaussian, as you might have heard it before. That's one of the most common ones, and we're going to talk about it quite a lot. So you see the density, and it's positive. Here's 0, here's 1, and yeah, it let's start here from the bottom. It adds up to 1. So if we take the area of the density, the integral needs to be 100%. Yeah, it is. If you just believe me, you can also like try and estimate it, but yeah. Then our function needs to be continuous. Yeah, is a nice line. I could just draw it with my pen. That's always a good sign. We can allow like a finite number of exceptions. This is more like a mathematical concern. You're just not allowed to like use super ugly functions that are kind of, you know, like everything that you kind of can draw with your pen and you kind of normally imagine will be fine. Yeah, it just can't be like too scattered like a fractal or something. And yeah, it needs to be positive and the probability needs to exist. Fine. Let's look at the CDF, the corresponding one. And I've just shown you a different function here. This one here is the PDF again. That's the density. And what I do is basically up to a certain point, let's say up to here, this is x. I calculate the area underneath here, and then this area gives me the point. Yeah, and we're here 0.4 or something. That's how the whole system works. And then if I go increase x, then the kind of the area increases, and we're kind of going up this line. Yeah, so this is the CDF. Because of that relationship, you can also say the steepness of the CDF. So if you kind of calculate steepness here with a little triangle, this one corresponds directly to the function of the PDF, the function value. Yeah, so the first derivative of your CDF equals the density function. Again, just like before, the CDF is monotonically increasing, yeah, because you are adding more and more positive density. So if you've got like this mathematical notation for it, if you've got 2 points and A is left of B, then the CDF at point A has to be lower than the CDF at point B. Yeah? Or they're allowed to be equal, that's also fine. So we start at 0 on the left and we finish at 1 on the right. Yeah, that's all the kind of conditions we need to meet. Okay, so that was fairly abstract now. So let's look into some examples. What could be decent PDFs and CDFs? So I've shown you 4 images here of PDFs, and which one of those could be a valid one? The other ones aren't, for one reason or another. Exactly. This one here, a little bit unusual, yeah, because it goes like back down to 0 here, but it is. The reason why the others can't is, let's look at 1. This goes from -2 to +2 and has a value of 1. So if I just look at this bit here, and that's not even the end, this has an area of 4. Yeah, can't be. So it violates that rule that the integral has to be 1. Yeah, all probabilities add up to 100%. What's the problem with number 2? Exactly, it's negative. Yeah, here's the axis. This is negative. Can't have negative probability density. There's no, yeah, it doesn't have any meaning. Same here, no? Negative values not allowed. Good. Let's go to CDFs. Which one of those cannot be a valid CDF? Perfect, yeah, number 4. All the others are fine. They all start at 0. They all finish at 1. They're all monotonically increasing, even if that one kind of does just one big jump. The only one that is kind of creating a problem is number 4, yeah, because it goes down again. Okay, let's look at the last example. So I've shown you a CDF here at the top, and which one of those functions at the bottom, which one is the corresponding PDF? Exactly, number 3. This one is not super obvious, but if you think of the steepness of the CDF at the top, that gives you the function at the bottom. So we're starting here on the left. If I, oh no, my pen stopped working, 1 sec. If you look here at the left, then we're fairly flat, yeah, steepness 0. So we need to, yeah, start the PDF also near 0. So that excludes this one here, which starts up high. And then what happens, like the steepness comes up, we're getting steeper and steeper and steeper. And then it's 0, we're at the biggest steepness, and then we get flatter, 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 and we'll go down to 0 again. So it can't be this one here, because that one would be flat, then instantaneously constant steepness, and then flat again. So it has to be between 1 and 3, and 1 has the maximum steepness over here at 1, and yeah, we need it at 0. So that's the winner here. Perfect. Good. So that was the first part. In the next part, we're gonna think about random variables and expectation values and variances. See you in a sec.